Near the end of Bohr's time at Manchester, he had met a friend who had been involved with spectra work and so on, and he was convinced that the spectra had to have some type of atomic cause. And this, coupled with Bohr's other learnings and work, ultimately sent him home to Copenhagen with the idea of taking the quantum idea and applying it to the hydrogen atom and seeing if Balmer's work could come out of it, that the success of this would work if Balmer's equation would fall out of his work. And so this is kind of the assignment that he went home with. And this work is, I think sometimes the way it's presented to young people isn't maybe as, it's a little bit misunderstood at times. I think Bohr's work's masterful. I really do. I think that he did a tremendous amount of work. It's not to say that it hasn't gotten better or there's been more to it. Of course there has. But there's a lot here, and I think it implied sometimes more than we let on. And I think also it gets misused. And so those types of things will be discussed in this video and in the subsequent video. So when Niels Bohr began his work, he went home to Copenhagen, and he decided to incorporate the quantum model, quantum idea, into a model of the hydrogen atom. And he had to base it on theory. And to start with, and a lot of guesswork, and this took 2 or 3 years, everything looks nice and elegant when you see it laid out in a textbook, but of course the real way things are figured out is far messier. So he made 4 assumptions. 1, electrons orbit the nucleus using circular paths. Now, this is just a guess. There's absolutely no evidence one way or the other. Atoms are very small. We don't see electrons. So, where was he getting this from, and why would this be something that he would choose? Well, the answer is quite simple. You're dealing with this brand new theory, and you're looking at, well, what's a simpler way we can look and see if there's any merit to this at all before we really spend a lot of time calculating things. Now let's remember, this is 1910, 1912. Calculating numbers was a lot of work in those days. We did not have computers, we did not have calculation engines, anything like we do today. Now let's just take, as young people, the distance around a circle is going to be, of course, 2 pi r, or pi times the diameter, something you learned in elementary school. Now, if we take an ellipse, a different shape, okay, and we say, okay, what is the distance around an ellipse? All we've done is squish our circle slightly, but what happens, and I'll draw this for you, okay, so we have our 2 foci, and we have an ellipse, like so. We've all done this, 2 pins and a piece of string, and we make this shape. And if you turn and tilt it, of course, you can make it a circle. So by just tilting the circle or squishing the circle, the distance around this not only moves away from an elementary formula like pi times diameter, but to calculus, and not only to calculus just per se, but to a calculus that we can only solve using a computer. So the perimeter of an ellipse is a difficult calculation. So the idea he had was, well, okay, let's keep it simple. We'll figure things out using circles first. If it works, then we can start worrying about whether it works for ellipses. I think that's prudent. He's not saying that the whole world works this way. He's saying, let's start here. I think that's good business. Okay, let's move to his second assumption. the electrons in orbit around the nucleus are in special non-radiative states. They only emit / absorb electromagnetic radiation when they change a state. This is probably one of his more controversial ones, but I think there's some to be said for this too. I think this was his initial idea of trying to explain line spectra, because if electrons only can emit or absorb between states, they're going to hop here or there, and you're going to have very specific energies. Anyhow, it sounds magic. Oh, gee, electrons just don't feel like radiating right now. Seems pretty lame. And also, the great Maxwell had taught us that if you have an electron going around a nucleus, so let's just do that one. So here's our proton. If we have an electron going around like this, okay, this is accelerated motion. And by Maxwell's work, this should imply radiative. Well, should be radiate. Okay, and this means it's going to lose energy. And so, if that happens, the electron is going to spiral in. But this is not observed. So while Bohr would not know the mechanism of what worked here, he said, well, gee, we're not seeing it. So there must be something going on. So let's put it in there. Now his last two laws are safer and less complicated. Number 3, conservation of energy. We had not seen a counterexample to that, so we felt he had to throw that one in. And 4, conservation of momentum. Specifically, in this case, angular momentum. Now this is concepts a little beyond grade 10, but what we're basically saying here is that the particle, if we think of it this way, think of figure skating, and a skater's doing a spin, and they pull their hands in and they spin faster. The skater's done nothing but pull their hands in and they go really quick. In the simplest way, we can say that the angular momentum is described as the mass times the speed times the radius. So when this figure skater pulls in her arms, because mass times speed times radius must remain constant in this example, if you pull in your arms, that reduces your radius, therefore the mass doesn't change, so therefore the speed has to increase. So there's an example of conservation of angular momentum for everyday use. And so these were his 4 basic ideas. Now since we're in grade 10, we're not going to derive this whole thing mathematically. But we do want to look at what he led it to, and maybe what his law said, and maybe what it didn't say. So Bohr's assumptions led us then to applying his non-radiative states and quantization so that only specific radii were permitted. And so we have our nucleus here, 1, 2, 3, and 4. What we found was transitions from 3 plus down to 2 gave us the Balmer series. From 2 plus down to 1 gave us the Lyman series, a different set of lines of hydrogen that are in the ultraviolet. From 4 plus to 3, we got the Paschen series, and these are in the infrared. Now it's interesting to think about this, because the hotter this atom is, the electrons would tend to be at higher energies you would expect. And yet the hotter it is, the less energetic the radiation, okay, because it's based on the gaps between these bands, not the total energy. When the atom is cooler, you get the ultraviolet spectrum. So it's counterintuitive. But that's all explained here very nicely. And the neat part about his mathematics was that, as hoped, he derived both Balmer's equation and his constant. Now, it's not very common that we find situations where a constant of nature is actually predicted by theory. We saw that with Maxwell predicting the speed of light, for example. Here was another case. It must have been very exciting. And it was very clear that everything falling into place so nicely with what Bohr did, that there was tremendous merit in this approach. Now, that's not to say for a moment we still have the circular orbits, we still have the non-radiative states, and this is all just guesswork, and yet it's working. And so we're glad, but of course this leads us to the concern of, well, why is that working? Okay, so we need to think a little more about this. So our story continues in 1916 with the German mathematician, a brilliant scientist in his own right, Arnold Sommerfeld. Who proved mathematically that elliptical orbits work for Bohr's atom. Now this has some import that I think we can approach as young people, just to show you where this can lead. When we do, you already know the force of gravity perhaps is equal to this equation. But the energy of an orbit is equal to a very similar expression. Now the A is the semi-major axis here, so that's from the center of the ellipse to the end. So we have Sommerfeld showing that elliptical orbits work for Bohr's atom. Now let's just look what that tells us about things that are going on. If we look at an example here in gravitation, we have the force of gravity equal to the universal gravitation equation, which you may have seen. If we have an object in orbit around the Sun, the energy of this orbit is expressed as minus GMM over 2A, where A is the semi-major axis. This is the distance from the geometric center of the ellipse, not the foci, out to one of the points, as I mentioned here. Now, what's important about this is that there's no information about shape. And so let's extrapolate this then to what we're doing with the atom. Well, the energy of the orbit is going to be a very similar calculation. The math is the same. We'll have minus an electrostatic constant, QQ, over 2A. And again, we have no shape information. Let's look and see what that tells us, or what it doesn't tell us, maybe, about where the electron can be. Because this is one of the problems with Bohr's atom, that the way it's interpreted is we forget that it can be elliptical. We deal with circles, and we deal with this planetary model, and it's not true. So here you have your nucleus, and we can have a circular orbit like so. We can have an elliptical orbit like this. And we could have an orbit that's somewhere in between, let's suppose. If I can draw this, do decency here. Okay. Now, in the case of the circle, the speed is constant. And that means that it's equally probable anywhere on its orbit. It spends as much time at any location in its orbit, and so it's equally probable. In this case, things, when we get out here, they're moving slower. Okay? In here, we're moving faster. And so what happens then is the particle spends more time out here and far less time in here because it is moving faster. Therefore, it is less time, more time out here. The more eccentric the orbit, the more that is enhanced. Now, in addition, because the Bohr information is only about energy, it's not about position. Okay, so a Bohr energy level, and that's what we need to remember, and that's well named, of course, is not equal to an orbit. So, in effect, we cannot know where the electron is. All we know is it could be one of these, so it's one of these shapes. Okay, and anything in between, of course. So now we can have a probability situation. Now, it can only get so close to the nucleus before it runs out, so there'll be a point where it cannot get any closer. And then there'll be a probability increase, and then a tail off. And it'll stop. And this is controlled by the number of possible orbits and the time it spends at a given radius. So we said with the circular orbits and things very close to it that they're basically the same. They don't move very much. And that represents in this fairly significant central point here. As the orbits become more eccentric, you're going to have encroachment towards the center, but they're not going to spend a lot of time there because they're busy. They're moving really quickly. At the other side, and probably with a slightly longer tail, we're going to have a much slower particle out here, which will spend way more time out here. But as the orbits elongate, there are less choices, there are fewer, it's less common. So what's important to sense here is that we end up with a probability distribution of where the electron can be. And that is something that was not seen, I don't think, ahead of time. But I think it's kind of a cool way to look at what this is telling us. Now, it's not exactly the uncertainty principle, but it's certainly a harbinger of the idea that where the electron is around the atom cannot be known so easily. Now, we have the energy levels and we can do spectra and everything else with them, but we have no immediate way to know what the shape is going to be, what the path is going to be. And this is really important to remember what we can say from Bohr's work and what we cannot say. So I would submit here we have a harbinger, at least, of probability of not knowing where the electron can be, and this density plot of where the electron could be, and that it is not uniform as you move out from the atom. Okay. Of course, this can be done in 2D. They don't all have to orbit in planes. They can orbit at any angle, so you'd have those additional complexities. So just some things to think about as we move ahead. The other thing that has been considered when we look at these things is that this is a distribution of charge, that the entire region is simply a smearing of one negative charge. The electron orbits the nucleus 10 to the 14 times per second, is moving so fast that you really can't see it as an individual particle anymore, and so you see it as this distribution of charge as well. Now this is, of course, in the 19-teens interpretation, 10 years at least before we got to more involved theories. But just some things to think about of what Bohr does tell us and what he doesn't tell us about his work, and I think that makes his work even more interesting. And there you have the work of Niels Bohr, and perhaps where it could have led. I don't say completely so, but I also think that he, if you extrapolate some of the ideas of what he did, I think you could make some suggestions that it was certainly leaning towards what we will see in the 1920s. It's still a very fine piece of work, and I think that given the time and the age and the circumstances, I think it was a very interesting piece of work. And of course, Bohr's study method was, of course, by talking things out. His significant writer's block and all the rest of it made it a bit more difficult for him. But whatever it is, everybody has a way of managing things. And this was Bohr's way of doing it. And his insight, I think, really made a difference. So anyhow, thank you for watching.